Hey everyone, welcome back. I'm continuing the interview prep. Let's go. Right, I'm now learning about data distributions. Data distribution, an important consideration before building a machine learning model is to understand what your distribution of the underlying data looks like. A lot of the algorithms make assumptions about how your data is distributed or how different features interact with each other. For example, almost all models besides tree-based models require your features to be on the same scale. Feature engineering can be used to manipulate your data so that it can fit the assumptions of the distribution, or at least fit it as closely as possible. Distribution assumptions. Almost every model besides tree-based models assume that your data, apparently tree-based models are different. So your data is normally distributed. Normal distributions follow a bell-shaped curve like shown here. The main characteristics of a normal distribution is that 68% of the data lies within 1 standard deviation of the mean, 95% lies within 2 standard deviations from the mean, and 99.7 3 standard deviations from the mean. Observing your data. To understand the shape of your own data, you can create histograms of each of the continuous features. To do so, once you have the matplotlib library loaded, along with your data frame, run hist on your data frame, followed by calling plt.show to observe the graph. Here we see the first column has a fairly normal looking distribution, but the second looks quite different. The majority of the data is skewed to the lower values. This is also referred to having a long right tail. Right skewed, left skewed. While histograms can be useful to show the high-level distribution of the data, it does not show details such as where the middle chunk of your data sits in an easily readable fashion. For this, you can use the box plot. Box plot shows the distribution of the data by calculating where the middle 50% of the data sits. This is also known as the interquartile range, or IQR. It sits between the first and third quartile, and marking it with the box. The whiskers extend to the minimum of 1.5 times IQR. So box plot distribution is 25th percentile, median, 75th percentile, and the interquartile range is 75th percentile minus 25th percentile, and 1.5 times the third quartile is going to be the, I guess, the maximum, the whisker, top part of the whisker. And then 1.5 times IQR, interquartile range. So Q1 minus that will be the bottom portion of the box plot. And then you have the outliers. Any points outside this area marked outside this are marked as outliers. This can be useful to also see if there are points in your data set that may be unwanted outliers. One final approach to looking at the distribution of data is to examine how different features in your data frame interact with each other. So how you can look at the data is you can build a histogram, look at the box plot, you can, histogram to see what the distribution is, box plot to see what the distribution is, and then you can look at how the variable interacts or is distributed relative to another variable, pairwise comparison, distribution of the data. Shouldn't have said that. There's so many things I shouldn't have said. So for our next meeting. Yeah, and then another one is to see how the different features interact with each other. This type of chart is called a pair plot and can be useful to see if multiple columns are correlated with each other or whether they have any association at all. To generate a pair plot, first you need to import the Seaborn package and then call the pair plot function on your data frame. In this example, we can see that the first and last columns are somewhat related. While all these plots are very useful to get an understanding of your data shape, you will at times want to quickly get summary statistics of your data's distribution. This can be found using the describe method as seen here on the same dummy data set we have been using to demonstrate the plots. Hmm. Perspective. Encouraging. Take a bad job. You had a rocky start. just started. Up until now, you have focused on creating new features and dealing with issues in your data. Feature engineering can also be used to make the most out of the data that you already have. I mean, you can keep doing it if you want, right? But again, it's not as you're making assumptions that is wrong. In my case, no one wants to listen to that. I mean, I don't. Don't give the limits. Don't talk about other people. You know. Forgive me, sinner. Up until now, you have focused on creating new features and dealing with issues in your data. Feature engineering can also be used to make the most out of you already have and use it more effectively when creating machine learning models. Many algorithms may assume that your data is normally distributed, or at least that all your columns are on the same scale. This will often not be the case. One feature may be measured in thousands of dollars and another will be in years. In this exercise, you will create plot plots, examine this some of the columns. Previously, you looked at distribution of the individual columns. Now, wow, this is a good start. A more detailed view of how different features interact with each other may be useful, as this can impact your decision on what to transform and how. When you don't have to transform your data, when don't you have to? Well, making sure that all your data is on the same scale is advisable for most. Just following machine learning models is normally not necessary. Decision trees. One thing I didn't get though is distribution can vary quite a bit. As decision trees split along a singular point, they do not require all the columns to be on the same scale. Interesting. All of it needs to be on the same scale? As mentioned in the last video, most machine learning algorithms require your data to be on the same scale for them to be effective. Is that really true? I don't know. Never heard it. For example, it is difficult to compare salary values with ages as shown here. Okay. While this assumption of similar scales is necessary, it is rarely true in real-world data. For this reason, you need to rescale your data to ensure that it is on the same scale. There are many different approaches to doing this, but we will discuss the two most commonly used approaches here. Min-max scaling, sometimes referred to as normalization and standardization. Min-max scaling is when your data is scaled linearly between a minimum and a maximum value. Never heard this before. Often 0 and 1, with 0 corresponding with the lowest value in the column and 1 with the largest. As it is a linear scaling, while the values will change, the distribution will not. Take, for example, the age column from the Stack Overflow dataset. The raw values lie between 20 and 80 approximately. While here, after min-max scaling, although the distribution is the same, the values sit fully between 0 and 1. So min-max scaling. So one thing I don't understand is you want the independent variables to be on the same scale, basically, for a lot of these prediction models. And so then one way to scale that, but I don't know where that's coming from. Like, is that even valid? Never heard that before. But yeah, so you make the minimum value to be 0, maximum value to be 1. And man, I feel so sad. It's just, you get so emotionally attached, you know? That's the danger of it. Yeah. First, need to import min-max scaler from scikit-learn's pre-processing model. Scikit-learn is the most commonly used machine learning library for Python. You then instantiate the min-max scaler and fit it to your data. This tells the scaler how it should scale values when it performs the transformation. Finally, you need to actually transform the data with this new fitted scaler. Note that as this scaler assumes the max value, it is created with is your upper bound. New data from outside this range may create unforeseen results. Okay, so now, and then you also have to transform the test data in the same way. Yeah, so that is interesting. When it, yeah, how do you deal with that? The other commonly used scalar is called standardization, as opposed to finding an outer boundary and squeezing everything within it. Standardization instead finds the mean of your data and centers your distribution around it, calculating the number of standard deviations away from the mean each point is. These values are then used as your new values. This centers the data around 0, but technically it has no limit to the maximum values, as you can see here. So min-max is you take the min and the max, and then from 0 to set it to 0 to 1, and then you, how do you even scale everything? And then you scale the rest of the data to fit that 0 to 1. However, if the test data has a range that is outside of the min and the max from your training data set, then it kind of messes up the data, messes up the predictions. It can potentially mess up the predictions. So another way of scaling and transforming the data is by using standardization, which is get the mean of your data centered around 0, and then divide by the standard deviation. So it's like xi minus x bar divided by SD of x. Yeah, that's how you standardize it. This centers the data around 0, but technically has no limit to the maximum and minimum values, as you can see here. You can apply standardization in a similar fashion to show how the min-max scalar was implemented. You first import standard scalar from scikit-learn, instantiate, and then fit it on your data. Once fitted, you can apply it to your data. Log transformation. Both normalizing and min-maxing are types of scalars. In other words, the data remained in the same shape, but was squashed or scaled. A log transformation, on the other hand, can be used to make highly skewed distributions less skewed. Take, for example, one on the salary columns from the Stack Overflow. Although it affects your data quite differently, a log transformation is implemented in Python the same way you have implemented scalars. To use a log transformation, you first import Power Transformer from scikit-learn's preprocessing module. Then you fit it to your data set, and once fitted, you can transform your data. Log transformation is a type of power transformation, hence the name. So log transformations are used if the data is too skewed left or skewed right, long right tail, long left tail. And it'll kind of make the data less skewed, yeah. Burning consider building a model is to understand what they do. I see. So almost all models, except tree-based models, assume your data is on the same scale. I did not know that. For multivariate predictions. Getting really hungry right now. As discussed in the video, in normalization, you linearly scale the entire column between 0 and 1, with 0 corresponding with the lowest value in the column and 1 with the largest when using scikit-learn, blah, blah, blah. Okay, in max scaler. While normalization can be useful for scaling a column between two data, it is hard to compare two scale columns if even one of them is overly affected by outliers. One commonly used solution to this is called standardization, where instead of having a strict upper and lower bound, you center the data around its mean, and calculate the number of standard deviations away from mean each data point is. Previous exercises, you scale the data linearly, which will not affect the data shape. This works great. What was that? Oh, it's scary. That is scary. That is scary. Anyways, which will not affect the data shape. When could you use normalization when working with the data set? When you know the data has a strict upper. Removing outliers. Man, I really just want to spend a week doing this. You often find that even after performing these transformations, your data is still very skewed. This can often be caused by outliers existing in your data. Outliers are data points that exist far away from the majority of your data. This can happen due to several reasons, such as incorrect data recording to genuine rare occurrences. Either way, you often want to remove these values as they can negatively impact your models. An example of the negative effect can be seen here, where an outlier is causing almost all of the scaled data to be squashed to the lower bound. watch elementary school or something like that. And we saw a commentary. Everyone has their demons. I think if converted into Christian terms, everyone has an insecurity. It's like I often try to do things that we normally wouldn't do, if we're insecure about ourselves. And I do that all the time. I feel bad about that. The fact that I can control it. What I'm saying is, I honestly believe that a lot of what we say or do is a result of your insecurities. Me knowing what should I do? Should I lash out? Be unprotected and understanding. I know why you're saying that. I understand. When you want to talk about, I get it. I'm sorry. It's so obvious. There is a piece of you that comments that. And it's kind of, if you step back and think about it, there's no reason to comment that. It's one. It's like shaking. Any moment, she'll call. But also, like, even if it works out, it's from the Lord. So I'm not going to be scared that you go to Korea, especially Korea is motivated by your insecurity. And of course, you'll say no, right? All of that. I think if you take time, be honest with yourself, be honest with people, and reflect, I would be surprised if you can say with a clear conscience that there is zero insecurity about that. Yeah, let me do some exercises. All right. Turn on some entertainment. The crazy thing is my blood pressure is 110/70. That's like the best it's been. Wow. Lord, help me to use good health for your glory. Anyways, let's get started. Okay. Just so sad today. So sad today. I don't know why. Well, I do know why. I'm going to trust in you, Lord. Not be anxious about it. Okay, quantile-based detection. The first approach we will discuss is to remove a certain percentage of the largest and or smallest values in your data. For example, you could remove the top 5% is achieved by finding the 95th quantile, point below which 95% of your data resides, and removing everything above it. This approach is particularly useful if you are concerned that the highest values in your data set should be avoided. When using this approach, you must remember that even if there are no real outliers, you will still be removing the top 5% values from the data set. Okay, to find quantiles, you could call it quantile method, standard deviation based approach. So you want to identify and remove outliers from your data. One way to do that is to take the quantile approach, and example is like 95th percentile approach. So anything that is above 95th percentile, a 0.95 quantile, you just remove it. But then the downside is even if they're not outliers, you're removing 5% of your data. Potentially unnecessary. An alternative and perhaps more statistically sound method of removing your outliers is to instead choose what you consider to be outliers based on the mean and standard deviation of the data set. For example, you may want to eliminate all data greater than 3 standard deviations from the mean, as you expect those data points to be outliers. This approach has the benefit of only removing genuinely extreme values. For example, if only one value was an outlier, only that value will be affected. Another way of easily removing outliers is 3 standard deviations above the mean or below the mean, you get rid of. Yep. So you can do that. And then percentage-based outlier removal. One way to ensure a small portion of data is not having an overly adverse effect is by removing a certain percentage of the largest and or smallest values in the column. This can be achieved by finding the relevant quantile and trimming the data using it with the mask. This approach is particularly useful if you are concerned that the highest values in your data set should be avoided. When using this approach, you must remember that even if there are no outliers, this will still remove the same top end percentage from the data set. While removing top 10% of the issue furnish disadvantage of always removing the same proportion of points, even if the data is correct. The commonly used alternative approach is to remove data that sits further than 3 standard deviations from the mean. You can implement this by first calculating the mean and standard deviation of the relevant column to find upper and lower bounds, and applying these bounds as a mask to the data frame. This method ensures that only data that is genuinely different from the rest is removed, and will remove fewer points if the data is close together. Three standard deviations. One of the most important aspects of machine learning is the actual application of it. For example, if you built a model based on historical data, ultimately you will want to apply this model on new data to make predictions. How you go about doing this depends on what transformations you make. To the data set before you fit the model. For example, if you applied standard scalar to your data before fitting the model, you need to make sure you transfer the test data using the same scalar before making predictions. Please do not use the scalar. Please do note that the scalar is fitted only to the training data. That is, you fit and transform the training data, but only transform the test data. Similarly, if you intend to remove outliers from your test set, you should use the threshold found on your train set to do so. If you were to use the mean and standard of the test set, it could negatively impact your predictions. Note that it is only in very rare cases that you will want to remove outliers from your test set. So why did we not refit the scalar on the test data or use thresholds from the test data to avoid data leakage? In real life, you won't have access to the test data. That is, when you have deployed your model in production, you won't have access to future data, so you can't rely on it to make predictions and assess model performance. Thus, you should always make sure you calibrate your pre-processing steps only on your training data, or else you will overestimate the accuracy. So far, you have created scalars based on a column and then applied the scalar to the same data that it was trained on. When creating machine learning models, you would generally build your models on historic data. Similar to applying the same scalar to both your training and test sets, if you have removed outliers from the train set, you probably want to do the same on the test set as well. Once again, you should ensure that you use the thresholds calculated only from the train set to remove outliers from the test. Similar to the last exercise, we split the SO numeric diff. All right. I think okay. So how do we handle missing data? You handle missing data in several ways. If you think it's done randomly, you can remove the rows with missing data. If it's columns, if it's a categorical or a string value, you can just input labels like missing or none or NA, something like that. If Yeah, and then if you think it's not random, so there is a good amount, and you want to keep the data, and it's a numerical column, then what you can do is input the mean, median, or the mode into the data set. But before you do that, you want to, but doing so can affect the mean or the median, or it can skew the data, the training data set, like the mean or the median or the mode. So before you do that, you want to calculate the test statistic um, and all the metrics, like the mean of the data set, before you actually input and replace the missing values with these data. And yeah. And really, I mean, you could also kind of make predictions of those missing values by doing something like clustering algorithms to see, the similar data set and see what kind of values they have. That's another approach. And you can also spend a lot of time figuring out which method is the best by evaluating the performance of the model with all these different variations to see what approach might be the most appropriate. Dimensionality reduction is beneficial because there could be a lot of redundancy in the data and or a lot of noise or just unnecessary data. Yeah, it could be redundancy in the data exists or columns that are not helpful. They're just noise. And so you want to drop these to improve processing times of the model, fitting the model. And also, if you remove the redundancies and the columns that are not helpful in making predictions, then it can improve the performance of the model as well. Yeah. Bias variance trade-off just means bias is, making assumptions about the data, simplifying it. Variance is overfitting the data. And so bias, high bias leads to simplifying the model to understand it better. But then you can miss the patterns and the relationships that may exist within the data. And variance means you're overfitting the data. So your estimates of the model can change drastically based on different training data sets. And so you want to minimize the variance, and you also want to minimize the bias. And bias, one way to think about it is bias is just skewness that exists in the data. So if you calculate the, let's say you take the, average or, average of the observed values. And then you take the average of the predictions, and the average of the predictions should more or less match the average of the observed values. But then if they're off, then you know that there's a bias there. When building a model using data science or machine learning, our goal is to build one that has low bias and low variance. We know that bias and variance are both errors that occur due to either an overly simplistic or overcomplicated model. Therefore, when we are building a model, the goal of getting high accuracy is only going to be accomplished if we are aware of the trade-off between bias and variance. Bias is an error that occurs when the model is too simple to capture the pattern. To reduce bias, we need to make, although making the model what is RMSE is just the root mean square error is to measure the performance of a regression model where root means squared error. So you calculate the error, and the error is calculated by predicted minus observed value, and then you square it, take the average of it, and then you take the square root of it. And obviously, the lower the root mean square error, the higher the accuracy of the model. Kernel function in SVM is just a transformation mathematical function that converts the data into a data that can be linearly divided, because SVM is a linear classifier where it'll divide the data set into I think 2 categories. I don't know too much about SVM. How can we select an appropriate value of k and k-means? So k-means is like you randomly choose center points in the data and see which center a point belongs to based on calculating the Euclidean distance. So the smallest Euclidean distance from the point to this one of the centers, it'll be classified as belonging to that particular center. And so, you want to go through a few, several iterations of the clusters being, randomly putting the clusters on in your data, identifying where which cluster each point belongs to based on the minimum Euclidean distance. And then you center the points, find the centers of these clusters, and then you run it again and again. You repeat this process until ideally the classifications don't change again. And then the question becomes, how many clusters should we have? And you want to obviously start with, whatever you think is best based on your knowledge of the data, but it's typically from 2 to any number. And one way to determine the ideal k-means clustering is using the elbow method, where for each k, let's say there's 2 clusters or 3 clusters or 4 clusters, you calculate the sum of calculate the sum of all the Euclidean distances that exist within the clusters, and then you see which k has the lowest. I mean, not which k, but where in the plot, and then you kind of plot, the sum of the distances on the y-axis, and then on the x-axis, the number of clusters. Then you kind of see if there's a drop, noticeably significant drop in the sum of the Euclidean distances. And that can be an indication of the number of k's, optimal number of k's. Another way is to use the silhouette width, which is you take a point and you calculate the Euclidean, you take the sum of the Euclidean distance, or you take the sum of the Euclidean distance of all the, of that point with all the points within the cluster that is identified as, and then you calculate the Euclidean distance of that point with all the other points that belongs to the nearest cluster, and then you use the formula, silhouette width formula. It'll range from -1 to +1, and you calculate that across all the points, and then you kind of see -1 means like that point probably should belong to the nearest cluster, and then +1 means that point should belong to probably belongs to the cluster that it's assigned to. And then when it's 0, it means it's a toss-up between one or the other. And then for different k's, you'll have different silhouette widths for each of the points. And then you just take the average. One way is to look at the average of the silhouette widths among all the points, and then find the one that has the highest silhouette width, and that'll also give you kind of that's another way of determining the appropriate k. How do we deal with outliers within the data set? Outliers can be determined in several ways. One way is to use the quantile method, which is you look at the data and everything within 95%, 95th percentile of the data you keep, and you get rid of the 5%. But then that may not be the best, because it's not necessarily the case that the top 5% belongs to, is an outlier. They may be legitimate data points. Another way is to look at 3 standard deviations above the mean, or plus or minus 3 standard deviations from the mean. Anything that sits outside of the 3 standard deviations from the mean, you can get rid of. Is that it? I guess there are other ways of dealing with outliers. Let me read it. I guess the question is, how do you deal with outliers, not how do you identify outliers? Yeah. So then how you deal with outliers is you can try transforming the data, scaling it. It could be log transformation. It could be standardized transformation. It could be a min-max transformation of the data, and see You could also consider choosing a model that is more resilient to the outliers, such as tree-based algorithms. Um, you can also scale, normalize the data, different types of model. That's it. Yeah, it's one way. Or get rid of them. Yeah, or get rid of the outliers. Yeah. Yeah. Oh man. Okay. Okay, I need to use the restroom. I don't think I did a full set here. Let me do one more. How do you calculate the accuracy of a binary classification algorithm using this confusion matrix? It's just you have on one, you have the confusion matrix, which is on one axis, you have the actual outcomes, right? The true, false, right? Actual, and then on the other axis, you have the predicted outcomes, predicted true, predicted false, and then so you have four boxes. One is true positives, one is false positives, one is true negatives. Well, I mean, one is false negatives and one is true negatives. And so you can calculate various things, right? Yeah, each box is like, number of predictions that are accurately predicted to be true. And then you have number, that's the true positives. And then the true negatives is the number of negative predictions that are accurately predicted to be negative. And the false positives are in actuality, they are negatives, but then they're predicted to be true, positive. And then the other one is false negative, which is false negative, which is they're actually true, but then you predict them to be negative or false. And then from that, you can use all kinds of metrics, come up with all kinds of metrics like precision, true positive rate, false positive rate, and accuracy to kind of gauge how well the classification model is performing. If there's a class imbalance, like most of the data is true, actually true, and only a small percentage is false, then you can look at the precision and true positive rate and false positive rate. But if it's a more balanced data set, you don't have to necessarily do that. You can just look at the accuracy, which is out of all the how many predictions that you get accurately right over all the data points. True positive rate, and this is so hard for me. Precision, true positive rate, false positive rate, super confusing, all of that. But um, a lot of these I can skip, I think. Come back to later if I have more time, but I gotta get the basic questions right, like simple linear regression and all of that. But I'll be back. Actually, I need to pack up. I should pack up. I do want to recite true. I think okay. So here's how I think about it. True positive rate. The denominator is actual positives, and the numerator is um, like how many did the model predict correctly that these are all positives. It's like when the wolf comes in, how many of the times does the model actually call wolf? False positive rate is the new denominator is all actual negatives. That's true negative versus plus false positives. And then the numerator is out of these, how many of false, true positive rate, false, true positive rate, and false negative rate. Yeah. False negative rate. Right. Yeah, false negative rate. No. False positive rate. Yeah. True positive rate, first false positive rate. So how many from all these negatives, how many does the model predict as positive? And you want the false positive rate to be 0 and the true positive rate to be 1. And then there's precision. Precision is the denominator is predicted positives. And among the predicted positives, how many are actual positives? And so it's like when the model calls wolf, how many of them are actual wolves, right? And you want all of these to be at optimal levels. And you can think of precision. To increase precision, you want to increase the classification threshold, right? You want to have more confidence that it's an actual positive before determining it to be positive. And then the true positive rate or recall or sensitivity is think of it as lowering your classification prediction threshold. Basically, if a wolf comes, you want the model to be able to detect that it's a wolf. So you want to just call as many wolves as possible. Positive, right? Wolf. Yeah. And then false positive rate is when there is no wolf, how many times does the model call wolf, right? So that's that. False positive rate. Yeah, it's all positive. Precision, true positive rate, false positive rate. Super confusing. All right. I think I'm satisfied for now. Do need to do a lot more, but yeah, I'm not gonna get to them. Yeah. Anyways, thank you everyone.